For topic 2, we're going to use the product rule for square roots to simplify square roots. So just as a really quick reminder, the product rule tells us that if we have the square root of a times the square root of b, we could rewrite that under a single radical as the square root of a times b. Similarly, we could also have a single radical of ab, and we could break it down into the product of two radicals, the square root of a times the square root of b. And this product, or this property rather, is really helpful when it comes to simplifying radical expressions. So right now we're specifically talking about square roots. Later we'll expand this to higher roots. But for now, this rule for square roots, the product rule, it allows us to simplify, and it kind of happens in two ways. Sometimes if you have two single radicals, they're both as simple as they're going to get, but once you multiply them under a single radical, they become something that you can simplify. So the individual radicals don't simplify, but their product under a single radical does. Similarly, you may have a product under one radical, but if you can break it up into two radicals, you can use that to help simplify. So this property is really, really helpful when it comes to simplifying radicals. Now, what does a simplified radical mean? Well, a square root, very specifically square roots for this video, a square root is simplified if the radicand has no factors other than one that are perfect squares. So here's our goal. Our goal is to simplify square roots by rewriting the square root as a product so that the radical has no perfect square factors. Let's think of something just really simple before we dive into our examples. Let's take 8, okay? Let's say we have the square root of 8. Well, 8 is not a perfect square, and that's okay. It doesn't have to be a perfect square, but I know that 8 is really 4 times 2, okay? Well, 4 is a perfect square, so 8 has a perfect square factor. So I could rewrite this as the square root of 4 times the square root of 2. Well, the square root of 4 is just plain old 2, and then we get 2 times the square root of 2. So this right here, 2 square root 2, and the square root of 8, they are identical. They are equivalent expressions, but we just say this one right here is simplified. We've taken out those perfect square factors, and let's prove it to ourselves. Let's prove that this really is true. So let's go to the calculator. Here. Yeah. So when we go to the calculator, we want to verify that 2 times the square root of 2 is exactly the same thing as the square root of 8. So remember, if you have this graph in calculator, you want to hit the blue second button. We go second and then x squared. That pulls up the square root symbol or the radical symbol. We put in an 8 as the radicand and simplify it. So the square root of 8 is 2.828427125, blah, 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 blah. It keeps going. Now let's see if 2 times the square root of 2 is the same thing. So 2, and then second, x squared, type in a radicand of 2. Let's see if this equals the same thing, and it does. So we've proven now that the square root of 8 and 2 square root 2 are equivalent. We've just simplified the square root of 8 into its simplest form, we'll say, which is 2 square root 2. So you always want to write it as a product so that the radicand, the radical expression that's left in the answer, is as simple as it's going to get, meaning it has no perfect square factors other than 1, okay? So let's practice. There are two ways to do this. Some students are really on top of their multiplication tables and they can just see these factors pretty easily. And for students like that, they can just jump right to it. Other students maybe need a little work finding those perfect square factors, and that's okay. We have a method that'll satisfy both needs. So let's look at example 2. We're going to have 2 examples in this video, example 2 and 3, each with multiple parts. So example 2, part A. We have the square root of 48. Now, if you're like on your game, you might be like, oh, well, I know 16 is a factor of 48, and it is. So we could easily rewrite 48 as 16 times 3. Well, we can now use that product rule for square roots and say, okay, well, we have the square root of 16 times 3, which we could just write as the square root of 16 times the square root of 3. And hopefully we're familiar with a lot of these perfect squares. The square root of 16 is 4, because remember, the square root of a number is one of two identical factors of that number. So the two identical factors of 16 are 4 and 4. So we would say, hey, the square root's just 4. Well, then we have the square root of 3. There's nothing we can do with that. The only factor of 3 that's a perfect square is 1, but that one doesn't count. So we just leave it in the answer. So we would say this is 4 square root 3. Okay, now let's say you just couldn't see that. You did not see that 16 was a factor of 48. That's okay. You're not lost. It's not like there's no hope. Okay, what we do instead is we create a factor tree. So a factor tree is where you put your number in question at the top. Almost think of like a traditional Christmas tree, and think of 48 as your tree topper, your little angel or your star on the tree. And then we're going to break down 48 as factors, where the factors are kind of like the limbs of the tree. So we need two numbers that multiply to give us 48. So let's say that we saw 2 and 24. Okay, well, that's great. 2 is prime, so we just bring it down again. 24 is not, so we find two factors of 24. Well, let's say we're like, okay, well, 24 is 2 times 12. Perfect. So we have 2 that we can bring down again. It's still prime. We have another 2 that is still prime. And then we have 12, which is not prime. So let's say we're like, okay, well, 12 is 2 times 6. Great, wonderful. Let's bring down our 2's. They're still prime. But then 6 is not prime, and it has factors of 2 and 3. Well, 2 and 3 are prime, so we now have 2 times 2 times 2 times 2 times 3. And we have to go back to that basic definition of a square root. So the square root of a number is one of two identical factors of that number. So what that means is we're looking for pairs of identical factors, okay? So remember, index for a square root is 2, so you're kind of always looking for groupings of 2. So we're looking for pairs of two identical factors. Well, I see a pair of 2's. This means a 2 can come outside the radical. I see another pair of 2's, which means another 2 can come outside the radical. And then this 3, it's kind of like the lone soldier. It can't pair up. You have to pair up to come outside the radical. So that 3 is stuck under the radical. So we have 2 for that first pair of 2's. We have the blue 2, which is the second pair of 2's. And then we have the square root of, make sure you put a 3 there, not a 2. The square root of 3. So let's simplify all of this. Well, 2 times 2 is 4, and then we get that square root of 3. There was nothing to pair up with that 3, so it has to stay under the radical. So either way you slice it, you can get to the answer. Now, this method right here is definitely going to be quicker. So if you see that perfect square factor that you can factor out, not factor out, but pull out, that's going to be quickest, okay? And sometimes you might find a perfect square factor, but then there's another one hidden in there. So you want to keep doing this method right here until you get down to the point where the radical has no perfect square factors other than 1. But that can be difficult for some of us. Some of us don't see those factors. So then we resort to this factor tree, okay? Let's look at part B. We'll do the same thing. We'll do it both ways. Okay, so for part B, we have the square root of 300. Now, hopefully you can see that anytime you have something hundred, so 300, 700, 1500, 2500, there's going to be a factor of 100. So we could rewrite 300 as the square root of 100 times 3. And then what that allows us to do is to apply the product property and rewrite this as the square root of 100 times the square root of 3. Well, the square root of 100, we should know we're looking for two identical factors of 100. That would be 10 and 10. So the square root of 100 is just 10. So this is going to be 10 square root 3. Square root of 3 is as simple as it's going to get. The only factors of 3 are 1 and 3, and 1 is a perfect square, but we don't count that when we're simplifying. So this simplifies to 10 square root 3. But just in case you didn't see that factor of 100, you can always resort to the factor tree method. Now, you don't have to do both methods. Just pick the one that you're the most successful with. But again, let's just say that you didn't see your 100 factor. So let's say we did notice that 30 could be written as, or 300 could be written as 30 times 10. Well, that's fine. So we've got two branches of this factor tree, 30 and 10. Neither of these are prime. So we're going to write 30 as 15 times 2 and 10 as 2 times 5. Well, that's great. So 15 is not prime. 15 could be written as 3 times 5. 2 is prime. The other 2 is prime, and the 5 is prime. So we've got a prime factorization, and let's look and see if we can find groupings of 2. Because with a square root, we're looking for pairs, like groupings of 2 identical factors so that something can come outside the radical. Well, right off the bat, I see a pair of 2's. So that means a 2 can come outside the radical. Even though they're not side by side, I see 2 5's. So a 5 can come outside the radical. And then underneath the radical, we have this lone 3. There's nothing to pair up with it. And the only way you can come outside the square root symbol is if you have another identical factor that you can come out with. So that square root of 3 just has to stay under the radical. So when we simplify this, we get the 2, we get the 5. So 2 times 5 is 10. And then we also have that square root of 3. So again, you can see here, we got the same thing with both of these methods. So you don't have to do both methods, just pick a method that works, okay? Now for part, this should actually say part C, that's a typo. So for part C, we have the square root of 39, okay? So let's say you're going through your mind and you're like, man, 4 doesn't go into 39, 9 doesn't go into 39, 16 doesn't go into 39, 25 doesn't go into 39, 36 doesn't go into 39, 49 doesn't go into 49. So you've gone through all these perfect squares and you've gotten to the point where you're looking at perfect squares bigger than 39. That should tell you that 39 just won't simplify. That's as simple as it's going to get. But let's say you wanted to try the factor tree. Well, you start going through and you're like, well, 2 doesn't go into 39, but 3 does. So that's cool. We've got a factor of 3. So we have 3 times 13. Well, the only 2 factors of 39 end up being 3 and 13, and they're both prime. They don't have there's no way to mate 13 or 3 with an identical factor and pull it out of 39. So this just further proves that the square root of 39 is as good as it's going to get. This one was already simplified. Okay, so make sure you understand how to simplify radicals. This is something that'll come up when we do something called, we're going to work with quadratics. So we've already looked at solving quadratic equations, but we're going to look at solving quadratic equations using this method called completing the square or the quadratic formula, and knowing how to simplify a basic square root is definitely going to show up, okay? Now, before we move on to example 3, which is still part of this video, I do want to bring your attention to this little nugget right here. It says a variable expression is a perfect square if the exponent is divisible by 2. Keep that in mind because that will show up in the next example, okay? So moving on to example 3, it goes along with topic 2, so using the product rule to simplify square roots. We have 3 more examples here. Well, one example, 3 parts. So next up we have 50x squared. So we have the square root of 50x squared. So hopefully with 50, you can say, what are some perfect square factors of 50? 25. 25 should be one of the big ones. So you could go ahead and think of this as the square root of 2 times 25 times x squared. We could then use the product rule for square roots to break this down. We could say this is the square root of 2 times the square root of 25 times the square root of x squared. And notice this has an even exponent. So it is a perfect square. And I'll explain how to simplify it in just a second. So we want to see of these 3 radical factors that we have here, which ones can we simplify? Well, I can definitely simplify this one and this one. This poor kid over here, though, it's as simple as it's going to get. Okay, so we're just going to have to keep that square root of 2 in our answer. So let's see what we get. Let's look first at the square root of 25. I know the square root of 25 is 5 because the 2 identical factors of 25 would be 5 and 5. So I get a 5. Now, when you have a variable expression under a square root, as long as the exponent is even, it can be simplified. So in this particular case, x squared simplify, or the square root of x squared simplifies as just plain old x. What you do is you keep the variable and you divide the exponent by 2. So 2, the exponent of 2 divided by 2 is just 1. So we get 5x, and then we still have that square root of 2 that cannot be simplified. So we would just say this is 5x square root 2. And that's it, okay? So don't get too bent out of shape if you have variables left over. or if you have variables in your square root, it works out fine. As long as the exponent's even, it's a perfect square and it'll completely come out of the radical. But in part B, we're going to look at a situation where we have a variable, but it is not a perfect square. Okay, so looking at part B, let's see what we can do with part B. So first of all, we have to address the 60. So some of you will be able to see a perfect square that comes out of 60 really quickly. But just for the sake of practice, let's say we're like, oh, is there a perfect square in 60? We don't know. So we're going to go to our factor tree. And let's say we were aware that 6 and 10 are factors of 60. So let's start with 6 and 10. Well, neither of these are prime, so we're going to break both of them down. We're going to say that 6 is 3 times 2, and 10 is 2 times 5. So all 4 of those factors are prime, so we can stop here and see if we have a pair that can come out. And we do. We have a 2 that can come out. So we're going to bring a 2 outside the radical. And then inside the radical, there's a 3 and a 5, neither of which have an identical factor pair that can come out. So under the radical, we're just left so far with a 15. Now we have to address the variables. So we have y to the third. So keep in mind that y to the third is equal to y times y times y. And remember, when we're dealing with a square root, we're looking for groupings of 2 identical factors. Well, we have a pair of y's. So that tells me a y can come outside the radical. But then this y right here, there's nothing to pair up with it. And if there's nothing to pair up with, it has to stay under the radical. So as weird as this one looks, this is the most simplified version of 60y to the third. And on my life, this is as complicated as I would make simplifying something like this. I'm not going to give you anything more involved than that. Okay, so if you can understand something like example 3, part B, you're good. Now for part C, we have kind of the opposite version of that property. So if we go back up here, remember I reminded you all of the property. We're looking at this version where we have 2 individual radical expressions that are both going to be simplified. They can't be simplified further, but if we can push it all under a single radical and do some simplifying, we might end up with something that could be simplified. So let's go back down here and see what's happening with part C. So if I look at 15, the only factors of 15 are 5 and 3. So there's no perfect square factor in 15. Same thing with 5. There's no perfect square factor in 5. 5 is prime. That's the only factor other than 1. So we're kind of stuck. Neither of these expressions could be simplified. They both have an x, but you'd have to have at least 2 x's for something to come outside the radical, and neither of these have 2 x's. So what we want to do is we want to try to push this all under one radical. So we're going to say, okay, this is 15x times 5x. Well, I'm going to take it one step further, and I'm going to rewrite my 15 as 3 times 5, and then I'm going to move my x's so that they're kind of side by side. So we're just kind of rearranging things right now. So we get 3 times 5 times 5 times x times x. And remember, when we do these factor trees, even though we haven't done a factor tree for part C, we're kind of doing the same thing. We're breaking this down into factors. When we look for a factor tree, we're always looking for pairs of 2 identical factors. Well, do we already have pairs of 2 identical factors? Yeah, we do. So if you look here, we have a pair of 5s. So that tells me a 5 can come outside. We also happen to have a pair of x's. So that means an x can come outside. So when we simplify this expression, after we pushed it all under one radical, things were able to merge and come out. So now we can say, well, a 5 and an x can come outside the radical. But this poor 3, bless its heart, it has to stay under the radical. There's nothing to pair up with it. It can't come outside. So our final answer would be 5x square root 3. So that is simplifying very specifically square roots, for example, 2 and 3. Later in this worksheet, we'll look at simplifying higher roots, okay, or higher powers. But for now, make sure you understand how to simplify a square root. I can promise you it will come up later in this course when we start solving quadratic equations using other methods. All right.